Awesome. All right. Thanks a lot for the introduction. It's great to be here and see so many familiar faces. So I guess those of you who know me probably know me because of my work in graph processing systems or stream processing systems. I do work very related to the previous talk. But what I'm going to talk about today is very different. It's a topic that is also new to me. I started working on this when I joined BU, and I'm extremely excited about it. I find it fascinating. So I hope you will also enjoy it. So I'm going to talk about efficient collaborative analytics with no information leakage, and I will try to convince you that this is a technology that is ready to be useful. So let me start by defining what is secure collaborative analytics, so what I mean by this term, and give you some examples of the motivating use cases that we're considering. So consider a set of data owners who want to perform some computation on their private data, but without revealing the data to each other or any untrusted entity. So such data owners can be, for example, healthcare providers who might want to do a large-scale medical study on union of patient databases, but without really exchanging the databases. Or they can be companies who might agree to allow computations on their employee salary datasets, but for example, to do a study on the gender or racial wage gap, but again, without revealing any information about their employees. Or it can even be end users, individuals like us, who are willing to provide personal data to an advertising company, for example, to train a recommendation model, but without compromising their privacy. Now, I guess it won't come as a surprise to any of you that security is expensive. It has an overhead. And if we want to do such queries, like relational queries, for instance, end-to-end secure, then we'll have to pay a big price. And here I just picked a few quotes and results from 2 recent papers on secure collaborative analytics to show you that end-to-end secure queries don't scale to more than a few thousand rows, really. So this is not practical. And our community has done a lot of work in making this practical, usually, or in particular, by finding interesting and smart ways to trade off security for performance. And here I will mention 2 main approaches that we have identified in this space. The first being information leakage. So the idea here is that we can allow leaking some information, maybe not about the original data, but about metadata, for example, leaking access patterns or intermediate result sizes, and this can give us a huge performance advantage. The second approach being computing on plain text data, but placing the computation inside a trusted execution environment like an enclave. And the third approach being requiring the data owners themselves to participate in the secure computation using their own trusted local resources. So having them actually participate in the secure protocol. Now, these are great approaches. The problem is that when we started talking to users interested in secure computation, and in particular, I'm talking about hospitals in the greater Boston area and companies like Bosch and Red Hat, we found that for many of them, this trade-off is a no-go. So essentially, even the slightest leakage is completely unacceptable, and they will not agree to participate in a secure computation. And sometimes it's even forbidden by law to leak anything about the original data. So let me show you a few examples of how these 3 approaches that I showed before can go wrong. So with regards to information leakage, there is a lot of research that shows how even the slightest leakage can lead to reconstruction attacks and may reveal sensitive data. So take, for example, this wage gap study that I mentioned before, and let's say we have a subquery that selects women managers within with a salary within a certain range. Now, knowing that this is a very small population of individuals, women in a manager position, if I leak the intermediate result size, not the result, but the result size of this query, I can potentially find identifying information about these individuals. With regards to data access patterns, again, let's say if I have an if statement, like the one that I show here, and I can monitor how many times this condition is true. For example, person 1 salary who is a man greater than person 2 salary who is a woman, then I can tell which of the companies participating in the study contributes the most to the gap, right? So these are 2 ways this can go wrong. With regards to hardware enclaves, I guess the main reason why these are not trusted is because they don't provide provable security. So there are many side channel attacks and other types of attacks that have been shown that enclaves suffer from. And the third point is something that was not very clear to me in the beginning, but requiring data owners to participate in the protocol is not always possible because data owners may lack the infrastructure or the expertise. So for example, a lot of the the hospital IT departments we talk to, they don't have the expertise to set up a secure computation, even if they have the infrastructure. Or you might have end users who don't have the infrastructure for deploying trusted resources. So that brings me to the core question of my talk today, which is, can we still achieve practical performance with provable security guarantees, meaning no leakage of any kind, in the outsourced setting, so without relying on any trusted resources? And as you might imagine, the answer is yes, otherwise this would be a very boring talk. So let me show you what we have been doing for the past 2 years at BU. So we're building a new relational analytics framework for secure collaborative analytics in untrusted clouds. We call this Secrecy. And Secrecy guarantees no information leakage without relying on any trusted resources and supports SQL queries. All right, so how does it work? Secrecy relies on a technique that is called secure multi-party computation to ensure provable security guarantees and no leakage. So what is secure multi-party computation, or MPC for short? It is a family of cryptographic protocols that allows mutually distrusting parties to perform arbitrary computations on their private data without revealing the data to each other or any external entities. And the way this works on a high level is that data owners take their data, split them into random data shares, distribute those shares to non-colluding computing parties, and then these computing parties follow a cryptographic protocol and collectively compute on their random shares any function without ever learning anything about the original data or intermediate data. And in the case of Secrecy, these computing parties can be, for example, competing cloud providers or resources managed by different entities in a federated cloud. So to make the guarantees more formal, Secrecy adopts a semi-honest model currently. And what that means is that we assume that the computing parties will not deviate from the protocol. They will follow the protocol, but they are still curious, so they can try to reconstruct data from their local random numbers. And we also allow an adversary who can monitor the network, all messages that are being exchanged, and can also compromise at most one computing party, but cannot alter its execution. And if these assumptions are true, then we provide the standard security guarantees of MPC, which are that untrusted parties will not learn anything about the original data or intermediate result sizes, and all data access patterns will remain hidden during query execution. Okay, so you might be wondering, this sounds like magic. How does it work? I was wondering the same when I started in the space. So I'll show you a very simple example of how we can do secure addition. So let's say we have two data owners, A and B. They each have a number, an integer, 5 and 4, and they want to compute the sum of their numbers without exchanging them. So they will split their numbers into 3 random data shares using arithmetic sharing. So that means that they will generate 3 random numbers that if you sum them up, they will give you the original number. And then they will distribute those shares, 2 of those shares in the case of secrecy, to 3 computing parties. So every party will receive 2 random numbers for each data item. And then using those random numbers, the parties can locally sum up their pieces, and they will end up with a secret sharing of the result. So they will have 2 random numbers that are pieces of the final result of the sum, right? So this is Secrecy's protocol. It's a replicated secret sharing protocol, meaning that each party on its own cannot reconstruct the data. If 2 parties collude, they can reconstruct the original data. Now, there are many more protocols. I will only focus on this one, but we can discuss more if you want afterwards. So having the shares of the result, now they can apply more operations like another addition or, for example, a multiplication. So the multiplication is a little bit more complex. The way it works is that, again, starting from 2 random shares, we have to compute this formula shown in the slide. So if we actually expand it, we will end up with 3 parts, 3 expressions that each party can compute locally on its random shares. And then they will end up with 1 random share of the result of the multiplication. And to maintain the replicated protocol, they will also have to send 1 message to another party so that they can receive the second share. And then they can perform another multiplication on top of that, or another addition, and so on. So having addition and multiplication, these are universal operations. So I can actually build anything I want on top of that. I can express any computation, including relational analytics. And this is exactly what we've done in Secrecy. In particular, other than arithmetic sharing that I just showed, we're also using another type of sharing that is called Boolean sharing, in which case, if you have a data item, you can split it again into random strings, bit strings, so that the XOR of the bit strings can give you the original number. So we also have corresponding XOR and logical AND operations. So XOR being local, exactly like the addition, and the logical AND being requiring 1 round of communication, exactly like the multiplication. So on top of those, we can then build equality, inequality, compare and swap, conversion from one type of sharing to another. And on top of those, we can actually go and build relational operations. So in Secrecy right now, we support selections, distinct, order by, group by with aggregation, join, semi-join, and any composition of these operators. All right. So something that is very important to understand why we have no information leakage with MPC is that all computation under MPC is oblivious. And what that means is that the computing parties perform computation that is data independent. So no matter what input you give to a computation, the data access and the operations that you perform are always the same. They don't depend on the actual data items, right? So recall that these are just random numbers, right? So it doesn't matter what the actual data is. The computation has to be always the same. And also data is not reduced. So for example, if I apply a filter, I cannot throw away the rows that don't match the predicate, right? I have to keep them around throughout my query, because if I throw them away, then I will reveal the size of the intermediate result. Okay, so I'll show you, for example, how we can compute an inequality predicate in an oblivious way. Right? So normally we would write if x greater than y, then do something. But in oblivious operators, we cannot have conditionals, we cannot have selection statements. So we have to transform this if statement into a formula that we can evaluate and get like either 1 or 0 based on whether it's true or false. And this is the formula for 3-bit numbers. It's much longer for longer length numbers, so I cannot show it. But essentially what this says is something very simple conceptually. It just says I'm going to go and compare bit by bit the two strings and check if the most significant bit is not the same, or the most significant bit is the same and the second one is not the same, or the first is not the same and the second is not, and so on, right? And you have to do this for the entire length of the input string, right? And this is the same computation no matter what the input is, right? Now, if you have inequality and you have equality, then you can apply predicates on tables. So for instance, if I have a table of employee and salary, and I want to compute a selection, let's say salary greater than 3,000, I will go and apply this formula row by row, and then I will get a secret sharing of a bit of a 0 or 1. Like the parties will not actually have 0 or 1, they will have a random number that if they put together, then they will get 0 or 1, right? And so I will append an extra column to my table that indicates whether this row belongs to the result or not. All right. Okay, so this is essentially, funny story, how we spent the first lockdown. Me and my partner here in Boston. So we started this project as a side project, and then we spent the entire summer and much of the fall implementing MPC primitives and operators entirely from scratch. And this is exactly what is Secrecy's main difference with compared to previous relational MPC frameworks. It's that by building all these primitives ourselves, we could understand the internals of MPC and we could optimize its execution end to end. So to give you an idea of how prior works used secure computation, they used secure computation as a black box. So essentially, you would have a query planner would optimize the query outside MPC and usually find a part of the query that can be run locally on a data owner, and then a secure part that needs to run under MPC, and then send the secure part over to a black box MPC library, which most of the systems use an MPC library that is called EMP. Now, this is great, but having the MPC library as a black box, you cannot really apply any database optimizations on the MPC part, right? And this is exactly what's different with Secrecy, is that we built an end-to-end secure MPC query engine so that the query planner and the MPC protocol, the MPC engine, are integrated into the same system, and we can optimize the query entirely under MPC. Okay, so here are the three main, let's say, contributions, novelties in Secrecy compared to the black box approach. The first one is that we rewrote all MPC primitives. We redesigned them to work directly on relations instead of individual records. And this makes a huge difference because If you use an MPC library as a black box, then every multiplication and every logical end operation will require one round of communication, right? So if you have a very complex formula to evaluate, that's a lot of communication. So essentially, by redesigning the primitives, we can amortize network I/O a lot. So, for instance, if we want to do, let's say, an inequality join, we have to compute this very long formula that I showed before for every pair of A and B. But in Secrecy, what we can do is we can find all the independent local operations and perform them in bulk, then find all the independent logical end operations and again perform them as a batch, which means that we can actually perform the entire join with log L plus 1 communication rounds in total, so independent of the number of rows in the input relations, right? Which is great because usually the communication is a bottleneck in MPC. So that's the first contribution. The second one is that exactly because we open, let's say, the MPC black box to the optimizer, we can actually now analyze the MPC queries in terms of we can analyze their cost in terms of MPC operations. And this is extremely important because, as I'll show you in a moment, if we try to apply plain text optimizations on MPC queries, these are not always effective, right? They don't work. So we defined 3 types of costs: operation cost, which is the number of MPC primitive operations; synchronization cost, which is the number of rounds; and composition cost, which is the extra cost of composing 2 operators. And this is not straightforward. So if you put 2 operators, if you apply an operator on the output of another operator, their cost is not just the sum of the individual costs. There is an extra cost for composing them. So this makes a huge difference under MPC because, for instance, if you take a common plain text optimization like filter push down, for instance, in this query, something that any plain text optimizer would most probably apply, under MPC this has no effect really. These 2 plans, exactly because the selection will not get rid of any input rows, these 2 plans will produce the same amount of tuples under MPC, right? So this is not effective. So we started looking into different database optimizations to understand, which are meaningful under MPC, which are not. And we found some of them that are effective. For example, reordering a join and a distinct operation is effective under MPC. So considering this simple query on the right, if we implement it with a plan on the left, that will result in n square log square n operations and log square n rounds under MPC, because the distinct needs to because the distinct is implemented with a sorting network like a bitonic sort. But if we push the distinct down, then we can lower the number of operations and the number of rounds. So we'll have log square n fewer operations, and that in practice is around an order of magnitude of improvement. So here I show you some results in the local area network with this optimization. Another one, another logical optimization that makes sense under MPC is decomposing join aggregation. So let's say we have a query that has an equality join on ID and then an aggregation on a different attribute of the left relation. If we implement this plan under MPC, we'll have to materialize the join result, because again, the group by needs to sort the output of the join. However, we can decompose the aggregation into parts, push a pre-aggregation before the join, and then essentially replace the join with a secure semi-join and partial aggregation. So for each ID in R, the semi-join will compute the number of times it matches with an ID in table S. And then we can have a group by operator to complete the aggregation by summing the partial counts of attribute A. And in this case, we can again reduce the number of operations and messages quite a lot, as well as the number of rounds from a square n square to linear, and the space from square to linear. And in practice, this results into 2 orders of magnitude better performance. All right, so we have analyzed many more optimizations. I don't have time to go over them, but essentially what I want you to remember as a takeaway is that by analyzing the costs under MPC, what we were able to do is actually develop a Volcano-style query processor, plug in the analytical cost model that we developed, and apply all these optimizations automatically. In addition to a set of physical optimizations and other protocol-specific optimizations that I will not cover in this talk. So here's the system architecture as of now. Secrecy is built in C++. It has a SQL interface, but also a low-level relational API that more expert users can use. It has a query planner, as I said, that applies all these optimizations automatically. And then on the computing party side, it has the Oblivious relational operator library. We have implemented the semi-honest MPC protocol that I talked about, and we are adding support for other even more stronger MPC protocols. The distributed runtime is based on MPI, and you can run Secrecy on any cloud federated data center or on-premises cluster. We have actually built an application to run Secrecy as a service on different cloud providers. So we currently support AWS, Google Cloud, Azure, and MOC, which is an open academic cloud here in Massachusetts. And the entire deployment is fully automated. Okay, so I only have a few more minutes left, I guess. So I'll just show you some more results. All right, so first of all, I want to show you what is the effect of all these optimizations. So this is a micro benchmark using all different queries that we found in prior MPC works. And we ran these queries with Secrecy optimizations on and off. With the only optimization that is on for baseline queries also being the message batching. So baseline queries also use message batching, otherwise they cannot even run on a few hundreds of rows. So on top of message batching, we can get 2 orders of magnitude speed up for logical and physical optimizations. And we can get up to 51 time speed up for when using the secret sharing optimizations. These are some rewriting tricks that we do because we know exactly how the protocol works. All right. The second result I want to show you is comparing Secrecy with this black box MPC library that prior works use. Unfortunately, none of these MPC relational frameworks is open source, so we could not directly compare with them, but we compare with the library that they use. But this library cannot support queries, so we instead compare 2 operators, so a join and a sort. So what I'm showing you here is an equality join, a cross-product join on an increasing number of rows per input. And EMP requires about 11 hours to compute the join on 4,000 rows per input, while Secrecy can execute the join on 100K rows per input in less than 4 hours. This is a local area network on AWS. And in terms of sort, I'm going to show you results in the wide area network, where Secrecy can sort 4 million rows in 42 minutes, while EMP needs more than 9 hours to sort the same input. So these are great. We also run Secrecy on increasing input sizes for different queries of 3 categories. So this is the easy one. This is an easy in terms of cost, MPC cost, because it only has selections and 1 global aggregation. So this is TPC 86, and it can go up to 8 million rows. And in the LAN setting, this completes in less than 6 seconds. Right, so this is very fast. And going to more complex queries, so these are queries with group-by and aggregation and semi-joins. Secrecy can again scale up to millions of rows. The most expensive of these queries is currency diff. It's the query shown on the right. And in this case, Secrecy can compute this query on 2 million rows in 1.2 hours. And these are even more complex queries. So these ones have, well, group, not group-by joins, group-by and several joins. And here we have results for TPC8, Q4 and Q13, going up to 300,000 rows per input, right? So these are extremely exciting results. So to put them in context, remember the slide I showed you in the very beginning, where aggregations and joins could only scale to a few hundreds of rows. And actually, these works report that joins on a few hundreds of rows might need days to compute. So we are very, very enthusiastic about this. And if you're still not convinced and you're thinking that, but this is still so slow, let me share a very important secret that I kept so far. That is that all the results I showed you are with a single thread per party and only using 32 gigabytes of memory per party. So most of these operations are actually very amenable to parallelism. So our main ongoing work right now is parallelizing this. And to give you a flavor of what we can do, I showed you sorting 2 million rows in 40 minutes. We've brought this down to less than a minute right now with multi-threading. So we can sort more than 2 millions of rows in less than a minute if we do this in parallel. So we're very, very excited. A few other directions that we are looking into is adding different protocols so that users can configure the security guarantees. The optimizations I showed are by no means exhaustive. So we've actually come up with many more optimizations, and especially if you can take into account the database schema. So if you have knowledge for about primary keys or foreign keys, you can do much more efficient joins. So these are things that we want to explore in the future. And finally, we have already started evaluating Secrecy in 2 real-world use cases. The first one is a medical use case in collaboration with BU Medical and the Hariri Institute of Computing, where doctors and medical campus investigators, they want to use Secrecy for doing digital health analytics on mobile health data. So they have collected data sets from users wearing wearable devices, and they want to curate data sets and share them with collaborators and even investigators outside of BU without revealing the patient data. And the second use case where we are deploying Secrecy right now is in collaboration with Red Hat, who want to do secure cross-site analytics on OpenShift logs. So the idea here is that Red Hat has multiple clients who run OpenShift on their local cluster. They want to have an easy way of identifying incidents, for example, bugs that show up with a particular version of Docker or some failure scenarios. And they want to do cross-site analytics on multiple clients. The clients, of course, don't want to share their logs because they're sensitive, but Red Hat wants to figure out as soon as possible, how frequent these incidents are so they can push bug fixes. So if you want to read about those use cases, I have the links in the bottom of the slide. I will conclude by saying that I'm just the messenger here. I did a lot of the prototyping, but the heavy lifting is done by John Lagouris, and of course this wouldn't be possible without help from Professor Mayank Varia, who's the cryptographer behind MPC. And I think this is an important message that we database systems people and crypto security people need to chat more. And of course, my brilliant second-year PhD student, Mohammad Faisal, who has rewritten much of my crappy code and made it run much faster, and a bunch of other bachelor's and master's students who have helped with Secrecy. So we have a technical report on arXiv that includes many more results and proof sketches and all the different optimizations that I didn't have time to cover. And I'm going to stop here saying that we are looking for people, both students and postdocs. So if you are interested, or if you know people who are interested, feel free to send them my way. Thanks a lot.